Hello everyone, my name is Ramesh Lama and currently I am working as a data analyst and researcher at U Energy in South Korea. Today I will be presenting my research entitled Optimal Power Generation by Controlling the Angle in Foldable Solar Panels. To give you an overview of today's presentation, we will start by exploring the fundamentals of solar tracking systems and its applications, and more specifically we will be discussing about agrivoltaic system. Next, I will introduce classification of agrivoltaic systems. Following that, I will introduce the proposed system framework and its benefits in terms of energy production and agriculture production. Then I will present the core part of our research, which consists of mechanical design of the proposed system, motor control, and finally angle control algorithm. I will then present the experimental results showcasing the effectiveness of our system and algorithm in real world scenario. Finally, I'll conclude the presentation with key takeaways and the potential implications of our research in the field of renewable energy. Solar energy is increasingly recognized as a viable alternative to fossil fuels due to its environmentally friendly nature. For the sustainable utilization of solar energy, optimal generation is essential. So solar tracking plays a crucial role in enhancing the power output and efficiency, and tracking systems adjust the panel's position throughout the day to ensure that they always directly face the sun, thereby producing optimal energy. So our aim is to design a solar tracking system that is particularly suitable for the agrivoltaic system so that the optimal energy is generated. And the agrivoltaic system represents an innovative merger of renewable energy and sustainable agriculture, offering a dual benefit of electrical power generation as well as the food productions. And if we see the historical development of agrivoltaic system, it can be traced back to the foundational concept proposed by Adolf Gottsberger and Armin Jastrow in 1982. While the initial growth was gradual, recent years have witnessed a rapid expansion in agrivoltaic system developed by different institutes. First agrivoltaic system started in France and Italy in 2011. Then we can see the government funding program started in Japan in 2013. And in recent days, numerous works are being done in different countries like China, USA, and South Korea. We can classify the agrivoltaic system into three types based on the priority of production. First one is the energy-centric system. This type of system prioritizes the solar power generation. The arrangement of solar panels is optimized for maximum energy captures, with the agricultural activities adapted to fit around these structures. And the second type is the agriculture-centric system. These systems prioritize agriculture activities and crop production. And in this type of system, emphasis is on maximizing the biomass production or food production, making minimal changes to existing vegetation management activities. And third one is the integrated system. This type of system offers a balanced approach, achieving the ideal equilibrium between the energy and crop production. These systems can be costly and complex to implement, and each system comes with the benefits and limitations. Like we can see, the energy-centric systems can lead to uneven shading, creating suboptimal conditions for certain crops. The focus of this kind of system might also overlook the agriculture potential of the land, because these kind of systems are more focused on energy generation. And agriculture-centric system often yield low energy production due to less optimized placement of the solar panels in favor of crop growth. And in integrated systems, these systems can be costly and complex to implement. Achieving the ideal equilibrium between energy and crop production remains a challenge. So to address the above these limitations in existing system, we propose an innovative method for the solar power generation using foldable panels, which are capable of collecting solar energy from both sides by tracking the sun's position. And our design integrates single axis solar tracking method to follow the sun's trajectory. By controlling the tilt angle of the panel, we aim to maximize energy collection from sunrise to sunset, and this is achieved by adjusting the panel to maintain an optimum angle relative to the sun's position throughout the day. And if we see the benefit, like we can benefit from the proposed system in terms of both agriculture production and the power generation. First, let's discuss the agricultural benefits. The use of foldable module design reduces the field obstruction, and to optimize the crop yield, it's necessary to adjust the shading rate according to the types of crops. The proposed system allows for the adaptive shading with the adjustable tilt angles, and during winters, crops can suffer cold damage at the down, and the installation of this system can mitigate such damage as the solar panels can block the downward flow of cold air during the early morning, and throughout the daytime the solar power generation and the crop photosynthesis can be conducted efficiently by controlling the angle of the foldable module. And during the midday of summer, the sunlight saturation point for the plant metabolism is often exceeded, making it necessary to control the angle of the solar modules, and adjusting the angle can block or partially block sunlight, achieving the shading rate up to 50%, and a shading rate between 20 to 30% is typically required for cultivating fruits and grain crops. By using foldable panels, we can adjust the shading rate to meet these specific requirements. And furthermore, the design employs minimum number of poles and allows for the adjustable height, which can accommodate large agricultural machinery to ensure minimal disruption into the farming activity. We can see here in the figure the case study of agriculture solar application, solar generation application in Japan. And in terms of energy production, our design employs a single axis tracking method to follow the sun's trajectory. By controlling the tilt angle of the panels, we can maximize the energy collection from sunrise to sunset, and this is achieved by adjusting the panels to maintain the optimal angle relative to the sun's position throughout the day, utilizing the dual panel configuration. And so we can collect optimal energy. And in country like Korea, where the land availability is limited, and areas suitable for solar generation are often already occupied by residential buildings, commercial sites, and agricultural land. Therefore, an agrivoltaic system can be most appropriate solution for the simultaneous solar power generation and the agriculture production. Now we'll be discussing about the core part of our research. We'll begin with the mechanical design of the proposed system framework. The mechanical design is shown in the figure, like we can see here. The leftmost figure shows the structure of foldable panels, and the rightmost diagram shows the angle control of the panels. We can see here that the panels are tilted at 10 degree, 30 degree, and 8 degree, and we use the DC motor to adjust these angles. And here we can see the figure displays the basic configuration of the motor controller. The motor control board performs static control, motor, limit detection, and feedback control. Basically, we use 24 volt, 4.6 ampere, 60 watt DC motor from GGM company, and For this we use the STM32 microcontroller, and this figure illustrates the whole configuration of the motor controller and overall control system. We can see here the main control consists of PC and RS-485 communication with the RTU. The computer communicates with the RTU through RS-485 and RS-232 protocols. Then the RTU, which includes STM32 processor, receives signals from different sensors like angle sensors, limit switches, and emergency switch. It also features the toggle switch to select between the automatic and manual mode, and we use SMPS for the power supply, and the controller board communicates with other peripherals either in unidirectional or bidirectional mode. Here we can see from the color of lines, like the blue lines indicate incoming signals, red line arrows indicates the outgoing signals, and the black arrows shows the bidirectional communication. And now I will explain about the control algorithm which is used to control the angle, how to control the angle or the adjusting the tilt angle of the panel, which is the core part of our system. Here from this, on the right side of this slide, we can see from the figure that our primary objective is to maximize the energy collection, and the panel collects maximum energy when it is perpendicular to the sun's ray, incoming sun ray. And in simpler terms, we set the angle at 89 degrees at the sunrise and sunset time, and to 10 degrees at the noon. When we gradually decrease the angle from sunrise to noon to 10 degrees, like we gradually decrease the at the sunrise time, our angle is at 89 degree, and then we gradually decrease it to 10 degrees till the noon. Then in the afternoon we gradually increase it until the sunset, and at the sunset it will reach to 89 degree again. And the rate of the angle change is determined by the fraction of total angle change relative to the total time from sunrise to sunset, and we calculate this fraction in two sections, like we calculate from sunrise to noon and from noon to sunset. And at sunset the tilt angle is like we can see the tilt angle will reach to 89 degree, and we prepare for the cycle to begin new the following day. So this is the overall algorithm of our system. And now our experimental environment configuration. Our experimental setup was established in the Suncheon city, where we installed both foldable and fixed solar panels to compare their performance. And we can see here in the figure, like the panel configuration is like the east facing movable panels were connected to the inverter labeled IME. The west facing movable panels were connected to the inverter labeled IMW. You can see that in this figure. And similarly, the east side fixed panels were connected to IFE, and the west facing fixed panels are connected to the inverter IFW, which also we can see here in the figure. Then we conducted our data collection in December 3rd of 2023. This involved recording the energy output from each set of panels and inverters throughout the day, and our focus was to compare the energy efficiency and output between the foldable panels with the angle control and the fixed panel without such control. And we can see the result here. This figure shows the power generation pattern of the installed solar panels. We can see here in the before 12 p.m. in the morning performance and the afternoon performance. The east-facing movable panels demonstrated, we can see here from the figure that the east-facing movable panels demonstrated the highest power output in the morning hours, like this yellow line, and this aligns with our expectation, like this worked as per our expectation. And it's because these panels are optimally positioned to capture the early sun. And at the same time, we can see the afternoon performance. The blue line indicates the afternoon performance, and here the west facing movable panels reach to their peak production in the afternoon, and this also indicates that these are effective. These are in effective alignment with the sun's position. And now if we see the overall power generation, like the total power collected by the movable panels exceeded the fixed panels, and this is the significant finding that it demonstrates the effectiveness of our control system, angle control system. And we estimated the total power generation ratio, and we found that 7.29% more power was generated by movable panels compared to the fixed counterparts. And we also tested the uniform power generation throughout the day by estimating the peak variance improvement ratio. For this, we selected the peak value of one peak value from two fixed panels and one peak value from two movable panels. And we can see here, like on the figure on the left side, it shows the power generation of all inverters, and right side shows the comparison of these peak values from fixed and movable panels. And we estimated the standard deviation of both graphs and estimated the ratio, and we obtained that ratio to be greater than 1, and that indicates that the uniform power is generated throughout the day. And now if we now in conclusion, we can say that the adjustable tilt angles of the panels not only optimize the solar energy capture but also allows the adaptive shading, and this particularly is beneficial in agrivoltaic system, and it optimizes the light exposure to meet the varying growth of the different types of crop. And the solar tracking algorithm, we can see like the solar tracking algorithm significantly enhances the efficiency of foldable solar panels by dynamically optimizing their angle to capture the maximum amount of solar throughout the day. And the incorporation of adaptive shading ratio not only increases the power generation but also presents the promising solution to agrivoltaic system, where the coexistence of agriculture and the photovoltaic is essential. And these results highlight the dual advantage of our system. One is enhanced power generation, and other is the improved agricultural productivity, and the increased energy and the potential for adaptive crop management make this system a promising solution to the suitable agrivoltaics system. Thank you.